Welcome to Techno Sapiens.
Welcome to this explainer. Today, we're going to take a really close look at one of the absolute wildest engineering hurdles our modern infrastructure has to battle on a daily basis. Every single time a major storm rolls through, millions of volts of raw electricity discharge from the sky and shoot straight toward the ground. Now, for a long time, lightning was just looked at as this spectacular natural wonder. But for the engineers out there who actually design and maintain our electrical grid, it's a relentless, super high-stakes threat. I mean, we rely on the grid for literally everything, right? From keeping our food cold in the fridge to powering the massive servers that run our entire digital lives. And as we depend more and more on this highly interconnected network, understanding exactly how it survives millions of volts of pure atmospheric energy is absolutely crucial. This isn't just about weathering a bad storm. It's about a heavily engineered system designed specifically to intercept and neutralize a catastrophic influx of power before it can plunge entire cities into total darkness.
So what actually happens when lightning strikes a power line? We know the power doesn't always go out, but a direct hit from millions of volts is a massive event that forces the grid to react instantly. And by instantly, we are definitely not talking about human reaction times. When we think of something happening fast, we might think in milliseconds, right? Well, grid defense mechanisms operate on an entirely different timeline altogether. They execute this highly choreographed sequence of events in mere microseconds. Electricity moves so insanely fast that the very moment a strike connects with the infrastructure, the battle is literally already underway. Understanding this microsecond by microsecond sequence reveals exactly how a localized point of impact is managed, ensuring the broader network doesn't just completely collapse under the strain.
Okay, let's dive into this. The immediate critical threat introduced by a lightning strike is what's known as a voltage surge. Your standard transmission lines and substations are very carefully rated for specific, predictable operating voltages. They have built-in tolerances, and the insulation wrapped around the wires and the equipment is designed to handle that normal flow of power perfectly safely. But a lightning strike? That introduces a violent, catastrophic influx of electrical energy that threatens to completely blow past those established tolerances. This overwhelming wave of power travels straight into the electrical system, desperately searching for the path of least resistance. It's an influx that fundamentally exceeds what the standard pathways were ever meant to carry. If this rogue wave of electrical pressure is allowed to just keep traveling down the line unabated, it will literally shred through the insulation and destroy the delicate internal components of the grid.
To combat this, engineers have integrated a dedicated defense mechanism, and it all starts with a crucial component called a surge arrestor. Think of a surge arrestor like a highly sensitive pressure relief valve, but instead of regulating water or steam, it regulates electricity. Under normal operating conditions, it just sits there, quietly, acting as an insulator and letting the standard power flow right past it. But the exact instant it detects a voltage surge exceeding the system's safe tolerances, its physical properties change in a microsecond. It catches that overwhelming surge and intercepts it. And the moment it does, the grounding system seamlessly takes over. The arrestor redirects that dangerous influx away from the main transmission lines and forces it down a heavy-duty, dedicated detour straight into the earth. By instantly shifting the path of the current, these two systems work in perfect harmony to safely dissipate that lethal energy, completely bypassing the sensitive equipment that keeps our homes powered up.
Now, if you happen to be standing anywhere near a transmission tower when this defense mechanism kicks in, it is a seriously intense sensory experience. The air suddenly smells sharp with ozone, there's a blinding flash of light, a surprisingly loud crack, and often sparks just showering down from the equipment. Instinctively, it looks and sounds absolutely terrifying. It gives you the distinct impression that a transformer has just exploded and the whole localized system is going down in flames. But the counterintuitive reality here is that this violent auditory and visual display is actually a sign of success. That blinding flash and deafening crack, that means the protection equipment is actively doing its job to isolate the fault. It's literally the sound of the system violently slamming the door shut to protect the rest of the network, willingly sacrificing a localized point or triggering a momentary isolation protocol, just to save the broader grid from taking the full brunt of the hit.
That instant fault isolation is the ultimate hallmark of a successful defense. It's what keeps the broader grid humming along smoothly even while a localized point absorbs a tremendous blow. However, there is a pretty stark reality when we look at what happens if a strike is simply too powerful and exceeds the absolute maximum threshold of those arrestors, or, say, a piece of older legacy equipment fails to trigger. When that overwhelming surge breaks through, the cascading effects are severe. The excess voltage will violently blow out insulators, practically melting them right off the poles. It'll breach the casing of transformers, completely destroying the complex coils inside. And this isn't just a brief flicker of the lights. This level of failure means intensive, time-consuming physical repairs. Crews have to go out, physically locate the blown equipment, safely tear out the destroyed infrastructure, and install brand new hardware. It's a whole process that inevitably leaves surrounding communities totally in the dark for hours, sometimes even days, while the physical network is rebuilt.
So, the crucial point is, lightning doesn't automatically destroy the grid. Given the raw, destructive potential of a direct hit, it's a super common misconception that a lightning strike is just a guaranteed death sentence for local electrical infrastructure. We naturally tend to assume that something so insanely powerful must inevitably cause a blockout. But the reality of our modern engineering is so much more resilient than that. As highlighted by researchers looking deeply into grid stability, lightning doesn't just automatically take the system down. The infrastructure all around us is not some fragile network just waiting to fail the second the weather gets bad. It is a highly robust, dynamic system built from the ground up to take a direct punch from atmospheric phenomena and just keep right on ticking. That durability is built directly into the architecture, hiding right there in plain sight.
And this brilliantly illustrates exactly what keeps our power systems alive, as outlined by the experts at TechnoSapiens. It really rests on three foundational pillars. First up is smart protection. We're not just talking about passive wires here. Modern grids use advanced sensors and relays that constantly monitor the flow of electricity. They intelligently determine exactly when and where to isolate a fault to minimize the impact on customers. Second, we have robust grounding. Every single pole, tower, and substation is meticulously tied to the earth, ensuring that when lethal atmospheric energy enters the system, it always has a designated, safe place to dissipate instead of seeking out your household appliances. And third is fast-acting equipment. This refers to the mechanical switches and breakers that physically separate the lines. They are engineered to operate in sub-cycle times, meaning they react in mere fractions of a millisecond. Together, these are the invisible shields actively working above our heads every day to keep the refrigerators running and the hospitals powered up through the absolute worst conditions.
Which leaves us with a really important consideration regarding the future of this infrastructure. We know that smart protection, robust grounding, and those sub-millisecond reaction times are what currently keep the system alive against some truly incredible odds. But we're also entering an era where extreme weather anomalies are happening with increasing frequency and intensity. It's basically an ongoing arms race between human engineering and the escalating power of nature. We really have to wonder if the existing tolerances built into our local grids are truly ready to handle the evolving threat of the next superstorm. Because as the climate changes and these storms grow even stronger, the engineering that keeps our modern world illuminated is going to be pushed to its absolute limits. Thank you so much for joining me for this explainer.